Welcome to today's lesson. I'm Siamasaka Kirian Dens. I'm going to take you through another interesting lesson where we'll look at linear momentum. And basically, we'll look at a solved problem where an elastic collision is involved as well as elastic collision. And then we'll look at also the energy, or precisely the kinetic energy that is lost during a perfectly elastic collision. And here we go. So as I indicated earlier, we have a question here which reads as follows. A 10 kg bag moving to the right at a velocity of 5 meters per second collides head-on with a stationary 6 kg bag. Find the velocities of the bags if the collision is elastic. B, find the velocity of the bags if the collision is perfectly inelastic. And also, we are asked to calculate the kinetic energy lost during the perfectly inelastic collision. So this is basically a simple question which I thought we'll go through, and we'll cover these three aspects for an elastic collision, perfectly elastic collision, as well as to determine how much energy is actually lost during a perfectly elastic collision. And so we'll start with the elastic collision. We are aware that during an elastic collision, both the momentum and the kinetic energy are conserved. So the kinetic energy before the collision, as well as the kinetic energy after the collision, is the same, as well as the momentum before the collision and after the collision, the momentum is the same. And so this is what is depicted here on these two equations I've written. The first part of the equation indicates that actually we have a bag with mass 1 moving with the initial velocity 1. And again, we have a ball of mass 2, which we assume that is moving with the velocity 2. And after the collision, we have mass 1, which will move with the velocity 1. And also the other bag with mass 2 will move with the velocity 2. And so also on the conservation of energy, you remember previously, if you look at the other lesson we looked at, we said kinetic energy can be solved using quadratic equations because it has a power 2. Or we can actually mold it such that it becomes a linear equation. And so what we solved the other time is we saw that actually making the kinetic energy into linear equation would give us the following. Initial velocity 1 minus initial velocity 2 will be equal to minus, in brackets, final velocity 1 minus final velocity 2 in brackets. And so this is the equation for kinetic energy, which we simplified so that it becomes also linear like the first equation here. This is very important because at times you may not need to actually use a rigorous method of actually solving this problem using the quadratic equation. And you can go straight and use this equation, which is simplified. And so we note that actually for the first part, the second actual bag here is not moving, and therefore this one becomes 0. It has a velocity, so this one becomes 0 here, as well as U2 here, the initial velocity for mass 2 becomes 0. And this is exactly what we have done here. We have merely indicated that the initial velocity for back 2 is 0 in this equation for momentum and also for kinetic energy. And so from there, we can make V2 the subject of the formula. So if we make V2 here, the subject of formula, this is what we get. We have just rearranged here. You take this one, this side, and then you divide by M2. This is actually what is here. Similarly, for this equation here, you can make V2 the subject of the formula. And this is what you get. You get V2 is equal to initial velocity 1 plus final velocity 1. And since V2 is equal to this and V2 is equal to, you can equate them. It means that this one is equal to this other velocity. And so this is what we have done here. And so then you can rearrange them by make sure that M2 here multiplied with everything here. This is what we have actually done. And this is what we get here. If this mass 2 multiplies with everything here, this is what we get here. And then we can actually put the like terms together. And when we put the like terms together, we can solve now for, because what we have here is actually V1, velocity, final velocity number 1. So since we have eliminated V2, so from here, you can actually rearrange. And this is what you get when you rearrange the equation. Find that velocity number 1 is equal to mass 1 minus mass 2 in brackets multiplied by initial velocity 1 over mass 2 plus mass 1. And you may now substitute the masses. Mass 1 is actually 10 kg and mass 2 is 6 kg multiplied by actually the velocity, which is the initial velocity of actually bag 1, which is 5 meters per second, over adding the two masses, and this gives you for final velocity number 1 as 1.25 meters per second. So this is very important because it's a concept that we need to develop here, which you can enable us to actually arrive at this solution. And basically, we have used the previous knowledge that actually the kinetic energy can be simplified. Instead of having a quadratic equation, we can simplify it into a linear equation and use this equation. And so we have calculated for velocity number 1. Now we can calculate now velocity number 2. Similarly, we have the first linear equation, which is this one here and this one here, okay, for kinetic energy, where we're saying kinetic energy is conserved. And this first one we are saying actually momentum is conserved. And realizing that actually the second bar was at rest, and therefore its mass will remain the same, but its velocity is 0. Similarly here. And so this is a simplified version of the equation after we eliminate the velocity of the second bar, which was at rest. And so we do the same now. Here, instead of making V2 as the subject of formula, we can make V1 the subject of formula. And this is what we have done here. Velocity number 1, make it the subject of formula. Similarly to this other equation, you can make velocity number 1 the subject of formula, and you get this one. And equate this one. You're going to equate this one that is equal to this one, because velocity 1 is equal to that one. Again, velocity 1 here is equal to this one. Okay. And so then the simplified version of the whole equation, as we did earlier on, would give us actually that velocity 2 is equal to 2 multiplied by mass 1 multiplied by initial velocity 1 over mass 1 plus mass 2. And you may now substitute 2 times mass 1 is 10 kg, initial velocity 1 is 5 meters per second over mass 1, which is 10 kg plus mass 2, which is 6 kg, and you get 6.25 meters per second. So basically, this is a simple application of the concepts for an elastic collision where we are saying the momentum is conserved as well as the kinetic energy is conserved. And so now let's look at the second part of the question where they ask us to find the velocity for a perfectly elastic collision. You are aware that for a perfectly elastic collision, it means that the two objects will stick together, they move together with a common velocity. And merely what we do here on this momentum, which we are saying is conserved, in a perfectly elastic collision, the momentum is conserved, but the kinetic energy is not conserved. And so we just say mass 1 multiplied by initial velocity 1 plus mass 2 multiplied by initial velocity 2 will be equal to the addition of the two masses multiplied by the common velocity, since they stick together or they move together. And we are aware that velocity 2 was 0 because mass 2 was at rest. And this is what the version of the equation that we come up with. And so we may now substitute what is applicable here. And we know that mass 1 was actually 20 kg multiplied by initial velocity 1 for mass 1 is 5 meters per second, and which will be equal to the addition of the two masses multiplied by the common velocity. And then the common velocity with which the two objects, actually the bags, move with, it means that when we make the subject formula, it gives us 3.12 meters per second. So merely here, the concept is that in a perfect elastic collision, actually the bodies, when they collide, they stick together. So they are going to have a common velocity. This is the basic concept that we need to know. And now we look at the last part of the question where they're saying also we have to calculate the amount of energy that was lost during a perfectly elastic collision. And we are aware now that the kinetic energy before the collision is equal to actually half mass 1 multiplied by initial velocity 1 squared plus half mass 2 multiplied by initial velocity 2 squared. Okay, and so you merely substitute now. We are aware that the mass 1 was 10 and the initial velocity 1 for the bag 1 was 5. So it's 5 times 5 plus half multiplied by the mass of the bag 2 was 6. And then you square, since this one 0, since this one was actually at, and you get 125 joules. So this is actually the initial velocity of actually bag 1, since we have eliminated bag 2, which was at rest. And so the kinetic energy of a perfect inelastic collision, it means that as well, the masses here should be added together. So we're going to have kinetic energy final for a perfect elastic collision to be half adding the two masses, mass 1 plus mass 2, since they move together, multiplied by the common velocity, which is the final velocity, squared. We merely substitute mass 1 is 10 kg, mass 2 is 6 kg, and multiplied by the velocity, the common velocity that we found actually, which was 3.12 meters per second. And this gives us 77.87 joules. And we have seen that as we proved the other time that actually there is a loss of energy during a perfectly elastic collision. And so the energy here, the kinetic energy here has been lost from 125 joules to 77.87 joules. And therefore we can determine how much energy has been lost here. We can merely actually subtract the initial kinetic energy minus the final kinetic energy, which is 125 joules minus 77.87 joules, which gives us 47.13 joules. So this is the amount of energy which has been lost. So we have proved that actually during a perfectly elastic collision, the energy is not conserved. So kinetic energy is not conserved. And so I thought these concepts are very important because we can apply them to actually more complex equations in linear momentum. I thank you. I urge you please to subscribe to my YouTube, as well as ensure that you follow these lessons so that they actually upgrade your understanding of physics. Okay, I thank you.